wire carrying a line charge density of lambda, which is 361 nanocoulombs per meter. Find the potential difference between points 3 meters and 6 meters on a perpendicular radius to the axis of the wire, provided the perpendicular radius is not near either end of the wire. Kind of a wordy way
You say it's very long.
to state it. It's very long, and you're somewhere in the middle region looking at the potential difference between point 3 meter, the 3 meter point, and the 6 meter point, finding your delta V. So the equation for the electric field is actually really easy to find. We could treat this wire as a whole bunch of point charges and integrate along the wire to find the potential here, but then we'd have to integrate again to find the potential here and take the difference. It's a little more cumbersome than just using Gauss's law to find the electric field. We have E times our area, which would be 2 pi RL. The charge enclosed, well, if we have a linear charge density, the charge enclosed by our area is just lambda L. So L is this arbitrary length here. L's cancel. E is equal to lambda over 2 pi epsilon naught R. If you remember, K was 4 pi epsilon naught R. So if we multiply top and bottom by 2, that is also an equivalent equation for the electric field. So that electric field basically only is valid under these conditions, so that the perpendicular radius is not near either end of the wire. So potential difference. If we have electric field between 2 points, then we have a potential difference. Delta V is equal to the negative integral of the electric field dotted with the displacement. So our electric field is K times 2 lambda over R. If we move radially outwards, then these are parallel, so the dot product only multiplies parallel components, so we're good there. Our limits of integration are our first distance to our second distance. Integral of 1 over R is the natural log of R. Plugging in our limits, we get the natural log of 6 minus the natural log of 3, which all of this is equivalent to the natural log of 2, because we get the natural log of 6 over 3. So we know K, 9 times 10 to the 9th. Lambda is given in the problem, 361 times 10 to the negative 9. Plugging that all in, we get negative 4,500 volts. Unit-wise, our K has units of Newton meter squared per Coulomb squared. Lambda has units of coulombs per meter. This term does not have any units. So that Coulomb cancels with that one, that cancels there. Newton meter per Coulomb is the same thing as a joule per Coulomb, which is the same thing as a volt. That's how the units work out. So the negative sign. The negative sign means this was our initial position, this is our final position. Getting a negative answer means the potential at the final position is smaller than the potential at the initial position. If you take a small number and subtract a bigger number, you get a negative answer.
Always drop.
Yes, so it's a drop as we move from 3 up to 6.
So since that wasn't a direction stated, we could have gone from 6 to 3, we got positive.
Yeah.
I also have a question. If you, okay, we were given lambda in this case. If you were given surface charge density or volumetric,
You just need to find your equation for the electric field in the region you're interested in.
but they're all going to end up with negative 4,500 volts, is that right?
Not necessarily, no.
Why would they be different?
Why would they be the same?
Because,
You get a completely different equation for the electric field if you have eta or rho. They're all different equations.
the reason why we use lambda is because all it is a
It's just a
something
line.
that doesn't have a surface charge or a,
Yeah, this is just long, thin wire, so it's basically a line.
so it can only have a lambda. Oh,
But yeah, if it was a surface charge density, you would figure out what the equation was for the surface charge density.
I guess my question is, if you have an object can have a surface charge and a volumetric density,
Well,
will
it can't have both at the same time. Your object's going to have one or the other. Your object's either going to be charged on the surface or it's going to be charged throughout the volume. You can't have both types of limits in the app. That make sense?
Yeah, that does make sense.
And
Now,
this-
you can have a solid cylinder that could potentially have either one, but in any one given situation, it's only going to
It's
have
either
one.
going to be an insulator or a conductor.
Yeah.
So something that's charged on the surface, would it be like an insulator wrapped in a conductor?
It could be something like that, certainly.
Or it just could be a regular insulator to be create heat. I mean, a
Yeah.
regular conductor to reach equilibrium.
It could be just a metal rod that's metal all the way through. It could be a hollow metal cylinder.
Well, wouldn't the rod, if it's a conductor, wouldn't the charge distribute evenly throughout the rod?
It's only on the surface. Whenever you have a conductor, if there were excess charges spread throughout the middle, there would be an electric field, and that electric field would make them move until they got to the outside, and makes the electric field go to zero. So on any conductor, the excess charge is always on the, once equilibrium's been reached, it's always just on the outside.
When is it insulator?
It'd have to be an insulator in order to do that. Now, an insulator can have a surface charge density as well. I mean, you can take an insulator and just charge it on its outside surface, that's fine. But an insulator can also be charged throughout its entire volume, whereas a conductor cannot. Other questions?
So when, I guess I'm still kind of jumping in, when a current flows through a wire, are all the moving electrons on the outside?
It depends upon what type of current you have. If it's AC, they are just on the outside surface.